Last time we started talking about hashing, and that turned out to be such an exciting topic that we couldn't handle it all in one sitting. And so here we are back for more. So let's pick up where we left off. Last time we learned about hashing schemes and hash functions and hash tables, and we learned about the ability to resolve collisions in a hash table using chaining. And we saw that chaining was a sort of convenient collision resolution scheme because even in cases where lots of different keys end up being hashed to the same bucket of your table, you can accommodate all of them. So whether that's because you just happen to have a worst case input sequence for lots of stuff ends up in the same bucket, or maybe you just have a lousy hash function and everything ends up in the same bucket, or maybe you haven't been maintaining the size of your table very well. Maybe you've allowed your load factor alpha to get unreasonably large. So you end up, for example, with 100 keys in a table with only 10 slots. Now, that's not recommended. I recommended last time that maybe you want to keep alpha somewhere around 0.6, certainly less than 1. But when we use chaining, it actually is impossible for the table to properly fill up. I mean, even in cases where every single bucket in the table has some list attached to it with lots of keys, we can always fit one more key in because these lists can grow to be as large as we want them to, as large as we need based on the constraints of our problem, based on how many keys get inserted. On the other hand, it's true that if we are not keeping the size of our table sort of well managed, if we're not trying to resize our table every now and then to keep alpha sort of small, we're not going to realize most of the real benefits of using hashing over some other kind of data structure. But that's up to us. I mentioned last time in passing that by using chaining, we are sort of, we get a sort of good excuse to turn a blind eye to certain factors that are important in hash tables, like alpha, like keeping our load factor relatively low, because we could just use a hash table with chaining for a long period of time without resizing, and until we start noticing a slowdown, until we start noticing an impact on performance, it doesn't appear as if anything has actually failed. And that's fair enough. I mean, that is, if we choose not to do the incremental maintenance, I guess that's on us. Although in practice, if I implement a table with chaining and I don't make arrangements for resizing, then a question should be asked of what I'm using a hash table for at all. There are certain special cases where I might want to do that, but it'd be up to me to justify that as the designer of a data structure. What I mentioned last time, though, is that because we're using chaining, we have to use some auxiliary structure to store the contents of each bucket. And logically, it sort of makes sense to use a linked list there. It makes sense that I need a structure that can grow in constant time, so I can add stuff to linked lists in constant time. And to be fair to linked lists, they are sort of lightweight compared to a lot of the other data structures we've seen. So I'd certainly much rather insert something into a linked list than into a heap or into a red-black tree, certainly. But on the other hand, we already know that linked lists do seem to have a lot of drag. They do have a lot of constant time overhead compared to, let's say, a plain old array. So way back at the beginning of the last lecture, when I was storing all of my keys directly in the array, although that did cause me a few headaches, one thing you couldn't say was that using an array by itself, having to index into an array, that was slowing me down. It was mostly the mechanics of what happens if two keys need to share an index. If we want two keys to be able to share the same index of the table, chaining is a great option for that, but bringing linked lists into the equation does add a lot of extra machinery. It adds a lot of extra overhead. And there are lots of cases where spatial locality can provide a huge performance advantage. Now, it really isn't our business in this course to worry too much about things like, what is spatial locality or what is a cache? But I've observed before that it's something that needs to be on our minds. It's something that from the point of view of any programmer, even back in first year programming, we should have it in the back of our heads that there are some choices we can make while programming that can have a performance impact beyond the obvious, beyond staring at our code and observing how many operations seem to be taking place. And we saw earlier in this course that if we choose to use an array, even though there are certain operations on arrays that are slower, that is in an asymptotic sense, or in a quite literal sense, like we actually have to spend time resizing arrays, even if that's the case, arrays themselves are sort of inherently rather efficient. It takes very little work to work inside of an array, and those advantages can pile up over time. So while there are still pathological cases, and there are lots of them where linked lists can be definitely way faster, there are quite a few cases where even though certain operations on arrays are slow, and you might be doing those operations, so a typical example we've used over the past 20 lectures has been, okay, so suppose I'm using an array to represent some sequence, and the size of the sequence keeps changing. Well, if this happens, then I might end up filling the array up. And if I want to resize the array to allow for more things to be added, I have to perform a copy operation, which on paper does seem quite slow. And in practice, it's going to be slow. I mean, in practice, if I have to copy n things, that's going to take linear time. But I observed way back in lecture 5 that there are lots of reasons why if we focus too much on that, if we fixate on that, we might not be seeing the bigger picture. There are lots of situations where, yeah, you actually can't spare that linear time. If every single insertion is happening under time-critical circumstances, then I can't allow any insertion to require linear time. If, on the other hand, you are willing to amortize the complexity of an insertion operation over lots of other operations, so in other words, you're willing to say, hey, I'm willing to take 10 insertions that are fast in exchange for one insertion that's slow, as long as the slowness balances everything out, well then in that case, using an array is actually a better idea than a linked list. Because if you resize carefully, so for example, if every time you resize, you double the size of the array, the total number of resize operations you need over time is very small, and each resize operation doesn't take that long in the grand scheme of things. So there are lots of reasons that arrays can be more useful in the pragmatic context of talking about linear versus constant time for insertion, as opposed to cases where, for example, it might be n squared. I've mentioned before that when it comes to making those trade-offs, just like the trade-off we make when we choose a hash table over a red-black tree, making a trade-off between constant and log n, or log n versus n, is quite a bit easier than worrying about the trade-off where I might have to accept n squared in exchange for constant somewhere else. Because n isn't that big. Linear time is something I want to avoid in searching problems, but if I can amortize it out, there are often cases where it's tolerable. So one of the other benefits of an array is that because it's in a contiguous block of memory, the caching structures that we tend to use in modern processors tend to be much better optimized for arrays. So in general, when you have a processor with a cache, and I'm not going to go into too much detail, there are other lectures you can go watch if you want to know about caching, in a processor with a cache, when I first read some piece of memory, suppose I read this index here, generally what happens is the processor pulls in the entire block of memory, some much larger chunk of memory containing my entire array, or at least a large chunk of my array, into the cache. Once something is in my cache, accessing it is really fast. The problem with a linked list is that if I have a linked list, the individual nodes were probably created at various different times. They were created through some dynamic memory allocation system, and therefore I have no real guarantee that they're all nearby to each other in memory. It could be that this node is sitting in memory block A, this node is sitting in memory block D, this node is sitting in memory block Z, and this one is back in memory block A. So if I access memory block A, everything in block A gets pulled into the cache. And that's great if I choose to access something else in memory block A. But if I iterate through my list, I end up looking at this next node in memory block D. Okay, maybe I go pull memory block D into my cache. But on the other hand, my cache has limited space. Maybe there's space for both block A and block D, so maybe I'll write that in. I'll put block D over here in my cache. Then I access memory block Z. And so eventually my processor's cache fills up, and my processor might have multiple levels of cache. Again, that's not really our problem today. This is a high-level example. But the cache will eventually fill up, and there's probably other things I'm accessing in memory besides these that need to be in the cache, and so I need to bring memory block Z into the cache. The way that typical caches work can mean that in certain cases where I'm allowed to put something in the cache is determined in advance, or there's a limited number of possibilities. Maybe when I bring memory block Z in, I have to throw memory block A out of the cache, so accessing it becomes slow again, so there's block Z in the cache. I keep iterating through my list, and now I'm back in memory block A, which I have to bring back into the cache. And the problem is, going to regular memory outside of the cache can be orders of magnitude slower than accessing something in my cache. So although the linked list is faster in an asymptotic sense, and that can be a real benefit in lots of problems, where what I'm doing on my array, if I have a massive array, for example, can really pile up over time. If I perform n linear time operations on a huge array, then the array probably will be way slower than a linked list. The issue is if I have, for example, a small array, maybe of size 10, maybe of size 1,000, the whole array might fit into a single line of the cache. And even if I have to shuffle values around inside my array of size 1000, if I'm working inside of the cache where things are orders of magnitude faster than they would be if I went to my plain old memory, then maybe the time of that shuffling doesn't really make any difference. Just like how I referred back in lecture number 18 when we talked about 2-3 trees, I referred to the fact that sometimes a generalization of a 2-3 tree, something called a B tree, is used in database systems, and the number of keys per node can be massive. It can be hundreds or thousands of keys. And that's because in a database system, maybe you don't care so much about processor performance, you care about stuff like storage performance. It doesn't matter if your CPU has to do a few extra operations, because the biggest bottleneck in your database is how long it takes to read something off of a disk, off of a persistent storage medium. And that can be so much longer than CPU operations take that you don't even care about CPU operations by comparison. They're basically just a dot on the map at that point. And so it's worth considering that. That's one of the reasons all this time, and I've mentioned this in various settings so far in this course, it's one of the reasons all this time that we have actually kept saying, hey, look, don't cut arrays out of your equation. Maybe arrays are a valid way of representing a sequence. Sure, we can use a linked list and it guarantees us constant time performance, and that's really important for us when we're proving theoretical attributes of algorithms, but in practice you might find that using an array is actually faster because our asymptotic analysis is biased towards really large data structures. So if I have, as I said, if I have an array of size 1 billion and I find myself doing a huge number of insertions and removals in the middle of the array, you can bet that a linked list is going to be faster. At a certain point, the advantages you get with arrays are negated by the disadvantages asymptotically of certain operations on arrays. On the other hand, if you're just inserting at the beginning and end of your array, or if you're inserting at the beginning and end of a sequence that you're storing in an array, because there are ways of representing arrays such that space is available at both the beginning and end, then the array might only have to grow sporadically, and over time, that growth, the cost of that growth can be amortized over all of the other insertions that you're doing. And so if your arrays tend to be small, where if I can fit an array inside of a cache line, then the cost of shuffling elements inside the array might be basically negligible. Or if the operations you're doing with your array, for example, inserting or doing a small number of element swaps and occasional rare growth operations, if those operations turn out to be relatively sporadic or constant time, then maybe arrays are better. Okay, so basically what I'm saying in all of this is we can't write off the possibility of storing all of our keys in the hash table as opposed to using linked lists. There are quite a few reasons why linked lists could be a performance drag that, although asymptotically might be better, in practice, especially with small hash tables, they might be enough to make linked lists not as good of an option as just using a plain old array. I'm going to come back to this at the end of the lecture because there actually is quite a bit of nuance to it, and it comes down to why you are implementing a data structure. So why do I choose to implement my data structure using chaining versus an alternative? Well, it actually comes down to what is the expected use case of the data structure? Do I expect to have billions and billions of keys? Or do I expect to maybe make a lot of hash tables that have size 100 or size 1000? We care a lot about asymptotic analysis because it's important to consider how things scale, but we can't write off the fact that in practice we often do create data structures that store a small amount of data. We already know, for example, that creating a red-black tree to store, I don't know, a collection of 10 keys is probably overkill. I could just use an array for that. The same reason that if I want to sort an array of 10 keys, I might just use insertion sort. I might not bother having to implement merge sort or heap sort or something else. Back when we talked about selection algorithms, which would have been, lecture 11? I talked about how you have to, in that BFPRT pivoting scheme, something that frankly is rather impractical and you probably wouldn't write in practice anyway, to be honest. When you go to sort those arrays of size 5, why would you use quicksort or merge sort for that? You're sorting an array of 5 things. At that point, even though insertion sort isn't asymptotically optimal, insertion sort is a pretty clean algorithm. It doesn't require that many operations if you're only sorting 5 things. The overhead of merge sort, the extra recursive calls, wouldn't be worth it. So so this is a case, the discussion of hash tables as a whole, our discussion of expected case running time last time, is a good occasion to question whether we want to do everything according to just one asymptotic quantity, worst case running time. It's still very important. I'm not backing down from that. I still believe worst case running time is a critical thing to understand when we're talking about algorithms, but it's not the only game in town. Okay, there I've gone and done it again, and I've gone on some tangent, or I've gotten way ahead of the slides. Let's just take a break and instead talk about the most pressing concern, which is before I can compare the performance of chaining to something else, I have to know what something else is. So my idea, the thing I want to start the lecture with, now that we're finally ready to start the lecture after 15 minutes, is instead of using chaining to resolve collisions, why don't we just, if we have a collision, let's just redirect whatever key we are seeing a collision with to some other open position of the table. Now historically, so we're talking about positions of a table because I'm drawing this diagram of an array in an abstract sense, but historically the first implementers of hash tables were thinking about positions in memory because, I guess the sort of archetypal example of an array is just your computer's entire memory. That is an indexable array. And so they didn't talk about open positions of the table, they talked about open addresses of the table. And so we call schemes that put every key inside the table, and in the event that you have a collision, they resolve the collision by just finding some other index to put your key. We call those schemes open addressing schemes because they go looking for an open address in the table. And the manner in which they go looking is what's called a probing scheme. And the idea is, here's your table, and you want to insert something, but this index of the table is full. What you do is you go looking in a few other indices. You probe other indices of the table. And if you discover that the next index is also full, you might go looking at this index down here. And if it's also full, you might probe some other index. And you keep probing indices until you find one that's actually empty. And that is where your new key goes. And so the key variable we have to address here is, unlike chaining, where there's pretty much only one way to do it, beyond a bunch of sort of clever advanced optimizations you might try, with open addressing, before we can talk about an open addressing scheme, we have to talk about how are we going to probe indices to find a vacant space. And there could be lots of ways of doing that. We'll start with a pretty simple one, and actually one that turns out to be pretty good overall. That is, we'll see that there are some bells and whistles we can introduce, and they seem to solve certain problems, but actually, in many cases, simplicity is a huge benefit. So we'll start with linear probing. In a linear probing hashing scheme, the first index we check, if we're doing a search or if we're doing an insertion, is the index that actually corresponds to the hash value itself. Now, if we're doing an insertion and this index is full, we just then look at successive indices afterwards. So h of k, then the next index, h of k plus 1, then h of k plus 2, and so on, until we find an empty space. Now, there is one assumption hiding in the background that I think is a pretty obvious one here, which is in an open addressing scheme, you are putting every single key into the table, so it physically ends up in the table. That means we have no choice but to resize the table if it fills up. We need there to be empty space in the table or we can't insert new things. And in general, we're going to assume in all of the examples we do today, and if you implement this, you should assume that you need to maintain the load factor strictly less than 1. So in open addressing, you need this all the time. There always has to be at least one empty index in the table because all of the search and insertion and removal logic depends on that. Even if you don't plan to do any more insertions, if you have alpha equal to 1, you'll discover when you think about the logic we're about to use for searching, that searching fails catastrophically if you don't have an empty space, because the search procedure can only end if the search is unsuccessful once an empty space is reached. So of course, it's incumbent upon the designer of an open addressing based hash table to ensure that the load factor is always less than 1. There's always at least one empty space in the table. Although, as I said earlier, frankly, I recommend that you keep the load factor somewhere around 0.6 or something like that, 0.5, 0.7, whatever, but keep a decent amount of empty space in your table. Okay, so when I'm using linear probing, I just keep checking successive indices until I find an empty one if I want to do an insertion. Or if I'm doing a search procedure, I give up my search once I hit an empty space. If I want to think about specifically a formula for which index I inspect at each step, in this case I'm numbering the steps starting at 0, so I is an element of 0, 1, up to, I guess, the table size minus 1, or maybe the table size minus 2. In that case, I'm just probing this index here. So h of k plus 1 all mod the table size. And I'm not going to write this mod in too many times in this lecture because it'll clutter things up a little bit. Okay, so here is a table using open addressing. I've already inserted a few keys into it. However, no collisions have happened so far. So up until this point, every time I tried to add a key, I was able to insert it directly into the index of its hash value. So nothing, you haven't missed anything interesting this far in the example. And the task is insert these 4 keys into this hash table using linear probing to resolve collisions. Okay, just to ease into it, the first one's going to be pretty easy. So the hash value of 5, h5, with this hash function here, and don't worry about doing this in your head. You should be able, by the way, to evaluate this very easily, but you don't need to because I'll make sure I print out the hash values every time I use them. The hash value of 5 is 4. I go looking for index 4, and you can see as of the beginning of the example, index 4 was empty, so I could just go and insert key 5. Okay, so just to remind ourselves what we're trying to do here. As soon as we find an empty index, that's where we perform our insertion. All right, now I want to go insert 35. So the hash value of 35 is 5, okay, but index 5 is full. This was the point in the last lecture where we had to give up. We just said our scheme fails, let's go find something else, and that's how we came up with chaining. But we decided here that we do want to cram everything into the table. So we now use our probing sequence to look at successive indices until we find an empty space. Okay, so the next thing in the probing sequence is the following index, index 6. That is also full. Okay, so we keep going. We then look at h of 35 plus 2, and we find an empty space. We look at index 7, and it's empty, so we insert key 35 at index 7. All right, it turns out that key 89 can be inserted directly at index 12. That's convenient. We then try to insert key 79. We're going to run into quite a bit of trouble here. So the hash value for 79 is 3. We go looking at index 3. It's full. Okay, so we start probing successive indices. We look at index 4. Nope, 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 nope. Okay, here we go. So after probing 5 different places, we end up finding an empty space at index 8, and we can insert key 79 there. Maybe you can already see a sort of characteristic issue we're going to encounter here, which is imagine what it must be like to go searching for key 79. Well, if I go searching, I start at bucket 3. I go look at index 3. But if I want to search, I have to retrace my steps. So any search has to follow the same logic as an insert process. That means that to search for key 79, I have to wander through all of these other keys. And those, I mean, that shouldn't surprise us too much. Even with chaining, you occasionally have to do a search that requires looking at a bunch of other keys. But notice how the keys I'm looking at in the middle here aren't actually hashing to the same index as 79. These are not collisions. These are just things that happen to get caught up in the same probing sequence as the thing I was just inserting. I might be getting a little bit ahead of myself again. I'm just too excited about hashing. So let's do a search for the key 18 in this hash table. So the hash value for 18 is 4. And so what I want to observe here is that, so h of 5 is equal to 4. So there is something already in index 4. It's key 5. And that's because 5 actually hashed into index 4. But none of the other elements of the table have collisions with key 18. That is, the only 2 keys in this table right now that hash to 4 are 18 and 5. All of the other keys we're about to see did not hash to index 4. Okay, so we'll do our search. Index 4 is occupied. So we go look at index 4, and it does not contain 18. So we keep moving. Okay, I then look at the next index, and what I have to do is follow the same probing sequence as I was for an insertion of key 18 until I can give up, because maybe if I did insert 18 earlier and it's somewhere along this probing sequence. The only way I'll know that 18 isn't in the table is if I keep probing until I hit an empty space, because if I had inserted 18, I certainly would have inserted it before any empty space. Okay, so I keep probing. 26 is not equal to 18 either, neither is 35, neither is 79, and then I get to an empty space. And because I hit this empty space, I know that 18 can't be in the table, because if I had inserted 18, this is where I would have put it. And so it's obviously not there. Okay, so the search was unsuccessful. And just like last time, as far as getting a feel for the running time of things, I'm going to focus pretty much only on unsuccessful searches. We know that a successful search will always take at most as long as an unsuccessful one, because an unsuccessful one is essentially a linear search and only can give up after considering all possibilities. If we had found 18 in the middle, we would have obviously done less work because we could have ended our search then. So notice that when I did this search for key 18, I had to progress through a whole bunch of keys that were not hashed to the same index as 18. They weren't hashed to index 4. Now 5 was. If I were using chaining, then I would have ended up with 5 and 18 being stuck in the same chain. And so it doesn't surprise me that I might have to look at both of them if I do a search. That's one thing I think that from seeing chaining first, we can sort of accept that, yeah, you're going to have collisions, and I guess it makes sense in a hash table that when you have colliding keys, your search procedure might have to look at every key that's in a collision before ruling out that a particular key is in the table. What's interesting is, although it looks from this example like things get worse with open addressing, by the end of this lecture, we're going to see that we can arrange things so they actually get better. We can actually have a shorter sequence of things to examine during a search, a shorter probing sequence in the case of open addressing, but a shorter number of keys that have to be checked than we would get in chaining if we arrange our hash table correctly. So what we just saw was an example of something called primary clustering. And you'll observe that if I do any search that puts me into any of these positions, then if it's an unsuccessful search, no matter where I start, so suppose I do a search that starts me in bucket 5, in order for the search to end, I have to progress through the entirety of this cluster before I get to an empty space. Even if nothing else in the table hashes to bucket 5, I'm only able to rule out, if I want to search for something that's in bucket 5, I can only rule out that it's present by looking at every single thing in the cluster. And the cluster contains a mixture of keys from different indices of the table. So it's called primary clustering when that occurs. And primary clustering is a sort of, I guess, like a distinctive disadvantage of linear probing. And often it's because the table might be too small or something. We're going to see later that linear probing actually has pretty good performance. But it's pretty easy to ascribe this problem to the fact that no matter where you start your probing sequence, the probing sequence looks exactly the same. So if I were to start probing here, the probing sequence looks like this. I just go ahead by 1. Okay, that's a pretty bad drawing. I go ahead in steps of 1 at each step. If I start the probing sequence here, I just pick up in the middle, but I do the same sequence of probes. I just move ahead by 1 at a time. And as a result, if you enter anywhere in this cluster with linear probing, you have to go through the entire cluster before you can rule out that the thing you're looking for isn't there. Let's try deleting something. I want to come back to the topic of clustering. I want to talk about deletion. We didn't spend any time at all pretty much talking about deletion last time because it's sort of obvious. In chaining, it's pretty clear how you delete something. You go find it and then you remove the node from the corresponding linked list. Here, though, deletion can be a bit tough. So there is an obvious, I guess, like a tendency for people to jump to a certain conclusion. Now, I know you would never do that because you're used to the sort of traps that I set in these slides, I guess, if nothing else. But there's a sort of obvious naive attempt to remove something that results in all sorts of trouble. So the question is, can we remove the key 5 from the hash table above? Remember that 5 hashes to index 4, and we can see that. So if I go searching for 5, I would start by looking at index 4, and I would immediately find it. So the hash value of 5 is 4. So my question is, and of course if I have to ask the question, the answer has to be no, is it a good idea to just clear that index? I went and found 5, let's just clear it out. Now the hash table has an empty index again. And the answer is no, it's a bad idea, you can't do that. And the reason is, let's consider 79 from earlier. 79 actually hashes to bucket 3, and I'll show that. I'll just scroll all the way back through my examples. So when I inserted 79, 79 actually hashes in to bucket 3, but I had to store it all the way down here because everything in the middle was full due to this cluster that had formed. So 79 belongs to bucket 3. If I go down and I delete 5 wholesale from my table, now what happens if I do a search for 79? So if I do a search for 79, 79 hashes to bucket 3, so I start searching. Well, it's not in bucket 3, so keep looking. Oh, I have an empty space, so I guess 79 is not present. But 79 is in the table. It's just gotten stranded over here because I interrupted my cluster by deleting an element. And unfortunately, the solution to this is you can't simply delete an element and leave the space in the table blank. Because if I do that, I'm breaking a connection that needs to exist. Although I don't necessarily have to have a 5 here, it's true that this has to be treated as a full index by a search procedure so that if I go searching for 79, I don't stop. I keep going until I find 79. So the remedy is actually I don't know, not very satisfying. So what I do, if I want to actually remove the key 5 from this table, is I delete it and I just fill the space with a placeholder. So there's my favorite invalid element marker that I've been using over the past few lectures. And you'll see I just use it more and more as time goes by. I just like latex symbols, I guess. So what I do when I perform a removal, if I'm using open addressing, is I go find the key I'm looking for, and then I just replace it with this invalid placeholder. A special, I'm going to call this a marker, denoting a missing key. So of course, now if I go searching for 5, it will not be found because 5 has been removed. But this is not considered a fully empty index. As far as a search is concerned, this is considered to be a full index of the table. And that way, if I go do a search for 79, I don't abandon my search too early. I do end up finding 79. So if I perform a search, the missing key marker is treated as an occupied index. Now, on the other hand, the missing key marker can be treated as an empty space during an insertion. So if I want to insert something and I start probing here or I start probing here, I am allowed to overwrite the missing key marker with a new insertion. So for example, suppose I want to insert 27 into this table. Okay, so 27, as it happens, hashes to index 3. Okay, but index 3 is occupied, so I start the usual process. I start probing. I probe index 4, but from my point of view, so index 4 contains this marker, index 4 can be treated as empty. So I can just insert 27 there. And notice that once I've done this, now the cluster has been restored. So if I go searching for 79, I will still eventually find it. And I've been able to leverage that empty space. So it was treated as an empty space during insertion, but not during a search. By the way, if I'm inserting things in a table where duplicates are allowed, then I have to be a little bit careful there. So of course, if I try to insert 79 into this table, then it's fine if duplicates are allowed, I guess. I can just insert it and have 2 copies of 79. On the other hand, if duplicates aren't allowed and somebody tries to insert 79, I guess you better check that 79 is not already there. So that's a separate concern for our purposes because it just comes down to an interpretation of what a dictionary is. And it comes down to, I don't know, how much you trust the person calling the insert function, so we're not going to worry too much more about that. The key thing is that missing key marker is critical to ensure that we don't break clusters that need to exist once we've inserted keys. So 79 is here, and we need to be able to reach 79 from our starting point of bucket 3. Now, I'm calling this thing, trying to be quite magnanimous and professional, I've chosen to call this thing the missing key marker, or an invalid element marker, or a special marker denoting a missing key, because those are nice, professional, mathematical sounding terms. In practice, you'll find that a lot of people refer to this marker as a tombstone. And I guess I sort of want to do that, but I'm a serious person and I don't say things like that. It is actually a pretty good term. It's nice to have spooky terms that we can use in math. And it's called a tombstone because, the element that used to be there is late to be deceased, I'm afraid. And also, if I were going to call it a tombstone, I'd go find a LaTeX tombstone symbol to fill in. Oh, it's so tempting, but we're going to call it the missing key marker. We're not supposed to be having fun. We're talking about hash tables. I'm already having too much fun talking about hash tables. All right, so in any event, when you want to remove something and you're using open addressing, in all cases, not just linear probing, you can't simply blank out an index of the table. Now, there are certain special cases where you can. I'm not going to worry about them, but you can think about certain special cases. So for example, if you wanted to remove 79 and you noticed that 79 was immediately before an empty space, maybe then you could fully clear out the index. But even then, you want to be very careful how you do that. So I'll leave you to think about those optimizations. For our purposes in this course, unless otherwise stated, every time I delete something using open addressing, I have to use the special marker instead. I can't simply clear out the space. All right, so I was talking earlier about clustering, and I want to go back to that. So in these examples, we saw that this is what's called primary clustering. And of course, you're savvy enough to realize that that must mean there's something called secondary clustering coming up. Just don't worry, wait for it. And so primary clustering is what happens if the probing sequences for different indices become fused together. That is, notice how if I start probing at index 4, this is my probing sequence. I wish I could draw these well. Okay, so You'll just have to, I mean, you see the nice typeset ones occasionally. There's the probing sequence for index 4. If I start probing at index 3, though, notice how after one step, I merge into the probing sequence for index 4. They all just get merged into one long probing sequence. And of course, that's problematic because maybe there's nothing else in index 3. Maybe only one key got hashed to index 3. I now have to scrub through all this junk that wasn't in index 3. Now, with open addressing, you are occasionally going to see keys that don't belong to your index as you probe. The problem is simply here with primary clustering, I'm literally looking at the entire probing sequence for index 4 when I start at index 3. I might, occasionally, sporadically hit some key that was supposed to be in index 4 while I'm probing through index 3. That by itself isn't really primary clustering. Primary clustering is where the entire probing sequence ends up absorbing the probing sequence from some other index. And of course, that's going to be bad performance because as we saw, literally any search that starts anywhere in the cluster has to traverse the entire cluster before getting out of it. Okay, well, the slides gave up there. Cluster, there we go. And so that's primary clustering, where multiple different indices probing sequences all merge together so you get trapped in there in any search. And the real problem with primary clustering, I mean, first off, the cluster forms, obviously that's a problem, but the problem with it is that the cluster can slowly grow to infect the entire table. Like, think about what happens if I insert some value at index 9. Okay, so now the probing sequence for index 3 is even longer. Every single probing sequence that starts in the cluster now gets even longer because of one element that I added. And notice how over time, if I keep doing that, I eventually end up with this one huge raft of keys that becomes one massive like mega cluster containing everything in the table. And so the problem with primary clustering is it's very hard to break out of once it's started, and it slowly grows to absorb everything. So that's obviously a problem. The question is there something we could do to fix it? I want to observe that before I talk about how to fix it, a couple of other cases. So one of them is, here is a table. I've changed my hash function to be something really obvious. Notice how, so it's k mod 13. So the hash code for 2 is 2. The hash code for 3 is 3. Notice how every key in this table gets its own index. That is, there are no collisions whatsoever. In my previous example, there were some collisions. For example, 14 and 79 had a collision. But in this table, there are no collisions whatsoever. Every single key currently in my table has a distinct hash value. However, suppose I go searching for key 15. Turns out that hash is to bucket 2. If I do that, I still have to search through all of these other things that had nothing to do with bucket 2 before I can rule out the presence of key 15. And so that's the downside of this primary clustering, and it is basically due to linear probing. Although, as I said earlier, we're going to discover at the end that linear probing is still pretty efficient, that actually we still get our constant time expected case search, find, and remove, or search, insert, and remove with linear probing. But that doesn't mean we can't find ways to improve it. So this cluster here formed even though there were no collisions at all. As soon as I begin searching where a collision does exist, so for example, key 15, I get stuck in the cluster and have to waste a bunch of time searching through keys that I have no business caring about if all I care about is bucket number 2. So one idea would be to say, okay, the problem seems to be, yes, obviously having lots of things next to each other is causing me trouble, but maybe I can't avoid that. There are always going to be collisions. I'm always going to have to worry about having to search through multiple indices in a hash table, whether I use chaining or open addressing. One characteristic aspect of linear probing that seems to be at fault here, again, is that idea that the probing sequence, the entire probing sequence fuses together. So here is the probing sequence for index 3. If I want to probe starting at index 2, I do one step, and then I just get stuck in the probing sequence for index 3. So how about this? To reduce the impact of clustering, because clusters could still form, let's use a probing sequence that somehow varies depending on where you started. So if I start at index 2, I probe a different selection of indices than if I start at index 3. Maybe they overlap to some extent, but not completely. So one way of doing that is what's called quadratic probing. And you can see here the probing sequence isn't just adding 1 at each step, it's going up according to the square of the index in the probing sequence. So step 0, you go 0 squared, step 1, it's 1 squared, then 2 squared, then 3 squared. And the idea here is the further you are into the probing sequence, the further ahead you're stepping at each point, which means hopefully you don't end up getting merged into the probing sequence for some later index in the table. Now, I should add a couple of things about quadratic probing. we're going to see in a few minutes that quadratic probing doesn't work in some cases. And I don't just mean that it's not helpful, I mean that it fully fails. And that means we should be very careful about when we use it. That doesn't mean it's bad, though. There are reasons quadratic probing is quite helpful compared to the next one we're going to see. Another thing I should observe is that depending on who you ask, the definition of quadratic probing can be different. So there are some sources, probably to work around that failure case that I alluded to a second ago. Maybe I won't draw this here. Some sources that define quadratic probing to be something more like this. Plus I squared. So although the step number is squared as part of the probing sequence, there may be other terms in it. So in that case, you could argue that they mean quadratic probing more like we're sort of evaluating a quadratic function of the step number, not just that we're computing individual squares. So you could do that. As usual, always read the label. So if you go read a different source about quadratic probing, be careful that they're using the same definition that we are. For the sake of our coverage, I will use this one. We'll just talk about the squares directly. So my idea here is that means that the probing sequence sort of diverges from my starting point a little bit. And that means if I start probing and I end up knocking into some other index, I'm not going to end up inheriting their entire probing sequence. And I'll try and illustrate that in the next few examples. Let's redo the earlier example. So here is, I've already done a bunch of insertions, but no collisions have occurred so far. Let's insert these 4 keys using quadratic probing to resolve collisions. Okay, so as before, 5 is a freebie. 5 just goes directly into index 4. If I try and use index 5, if I try and hash the value 35, it comes to index 5, which is occupied. Okay, so I start probing. Okay, so the first thing I probe in my probing sequence after the initial index is h of 35 plus 1 squared, which would be index 6, but that's also full. The next one I do is h of 35 plus 2 squared. So that would be a distance of 4 from my initial starting point, but actually a distance of 3 from the most recent place that I searched. And we'll notice that in this case, it actually is empty. Although frankly, even if we were doing linear probing, it would be empty because we just checked the next bucket. All right, so again, the hash value of 89 happens to be 12, which in this case is empty, so that's also a freebie. We just insert it directly in index 12. Now, I try to insert 79. Now, recall that last time, because 35 ended up here, last time 79 required quite a few hops before I could insert it. Hopefully, quadratic probing helps us with that. Although, as usual, even if it does, that doesn't necessarily mean quadratic probing is always better. It's just an anecdotal example. Okay, so index 3 is occupied, so I check index 4. That's also occupied. So now I move ahead by 4 steps from my initial starting point, and I hit index 7. Great. So I only had to probe 2 other places before I got to my result. Notice that I did have to step on something that didn't go into bucket 3, but that's a fact of life. If everything's going to have to share the same table, I will expect that in my probing sequences, I may see keys that weren't hashed to the same place that I started. But notice that once I hit bucket 4, I didn't end up absorbing into the probing sequence from bucket 4. So if I start probing from bucket 3, I first go to 4, and then I go to bucket 7. If I were to start probing from 4, I would actually go to first bucket 5, and then I would go to bucket 8. So notice how the probing sequences do diverge. They depend on their starting point, so I don't end up getting sucked into the probing sequence for the next index like I would with linear probing. Let's try doing a search. Okay, so I search for the key 18. So 18 hashes into bucket 4. Okay, index 4 is occupied. We already know this. It doesn't contain the key 18, so I proceed through my probing sequence. I check bucket 5. 18 is not there either, so I check bucket 8. And notice that because quadratic probing, the probing sequence increases its step size over time, I don't worry about any of these. They're irrelevant to me. I go to bucket 8. Bucket 8 happens to be empty. And of course, if I'm maintaining my load factor to be close to, let's say, 0.6, I'm keeping a healthy number of empty spaces in my table, then I can reasonably expect that I should hit an empty space pretty quickly in my probing sequence, which I do here. And so the search, which is unsuccessful, can now terminate. Now, one thing I will observe, I won't bother with an example of this because, well, also I want to make it an exercise, is that there is a bit of a hazard with quadratic probing, and it comes from a property from number theory that, again, is sort of outside our context. We've seen over the past couple of lectures that hash tables rely on a lot of complicated mathematics outside of our usual scope, so not general discrete math stuff, although I guess the pigeonhole principle counts as discrete math. We've had to use some probability, which we do know about, but we also need to know a lot about number theory to explore explore some of the deeper properties of hash functions, and we do not want to talk about number theory in this course. It turns out that due to some number theoretic thing relating to the way that squares work under the modulo operator, so if you're working modulo some number and you're talking about squares, it turns out that that can result in quadratic probing in the event that your table size is not a prime number. So everything's good if your table size is prime, and 13 is prime. If you chose a table size of 10 or 16 or 32, you might get yourself into trouble. And the reason is because the probing sequence produced by quadratic probing may not actually visit every index of the table. I can't really model that with a table of size 13, but basically what happens is you might probe 0, then 1, then 10, then back to 1, then back to 0, then back to 1, and then 10 again. So in other words, for some reason, quadratic probing only results in a certain set being inspected, which means there might be empty spaces in the table that quadratic probing never finds. And if that happens and you go to insert something, the probing scheme might just enter an infinite loop. And even if you try and catch the infinite loop, the best you could do is to say, sorry, I couldn't find an empty space. And we saw last time, if there is an empty space and you're unable to perform an insertion, then the scheme fails. And that means you just don't have a dictionary. It's just a complete failure. It's a write-off. So keep that in mind. Now, it only is a problem if you're using quadratic probing on a table whose size is not a prime number. If it's a prime number, everything's good. In some cases, even if it isn't a prime number, maybe everything is going to be good. And maybe you find an empty space, but be careful about it in that case. I would say do not use quadratic probing unless you guarantee your table size is prime. Now the exercise is, consider, because we don't want to prove this in general because that would require the number theory that go take a number theory course. They're really interesting, but we can show it specifically. So look at a table of size 8 and just try a couple of examples. So for example, try inserting a few things that all collide with each other, and you'll notice that eventually quadratic probing doesn't actually find an empty index. It just keeps bouncing around the same set of full indices for eternity. And of course that means the scheme fails. Now, let's go back to our discussion of clustering. So because the sequence of indices that I probe depends on the starting point, I don't have to worry about that problem with primary clustering that I had before, where if a bunch of things end up next to each other, I'm doomed to have to traverse all of them if I want to do a search. I might have to traverse some of them, that's not a big deal, and primary clustering can still affect quadratic probing if it gets really bad. So if I fill all of these indices, and I think about quadratic probing starting at index 3, I would start with index 4, then I would go to index 7, and that's also full. And I can imagine that, yeah, if the cluster gets large enough, then yes, quadratic probing is still sensitive to primary clustering, but not nearly as sensitive as linear probing is. And so even if we have a cluster, because of the larger step sizes, I can expect that I can escape from that cluster pretty quickly. So if I jump 1 and I'm still in the cluster, and then I jump ahead by 3, so I go ahead by 4 from my original point, I'm still in the cluster, well, my next jump is going to be by 8. And so I just keep jumping larger and larger amounts, which means I should get out of the cluster pretty quickly. Now, let's consider this hash table here. So I've again chosen a very simple hash function, and what I have are a sequence of keys that all collide with each other. So this is our hash function from last time that just used the last digit of my key as the index. And you can see that every single key ends in a 1 here. So in fact, every single one of these things actually hash to the same index. And I've already inserted all of them using quadratic probing. Now let's consider what happens if I do a search. So I'm going to search for the key 71, and 71 is not present. Okay, so it hashes to index 1. It's obviously occupied, so I'll go through the full animation either way. I then look at index 2, that's the next thing in the probing sequence, also occupied. Then index 5, also occupied. Then index 10, also occupied. Okay, so the next one, I'm going to be jumping ahead by... I'm going to be going ahead 4 squared. That's actually going to wrap me back around and put me down here. So the arrows are going to begin to overlap. I look at index 4. Okay, that's also already occupied. Then index 0, already occupied. And finally, after looking at literally everything in the table, I hit index 11, which is empty. So at this point, I can say, okay, 71 is not in the table. So what happened here? Well, I guess I ended up in a cluster. And that shouldn't surprise me. The same thing would happen with chaining. Every single key in this table hashes to index 1. So with chaining, I would just be inside of a long list of things at index 1. And this is a form of clustering as well. This is typically called secondary clustering. So primary clustering is when the keys in a bunch of different indices they run together to form some huge mass of keys that you get stuck inside of. And that is what linear probing is susceptible to. What we're seeing here is the same kind of clustering we would see with chaining. Now, I tried not to call it clustering in the last lecture because I figured that if I said clustering, I'd have to explain that I'm talking about secondary clustering. And it feels like that's a bit of a dirty trick to tell you about secondary clustering but not tell you what primary clustering is. So I tried to save that definition for now. So what we have here is simply that because I have a whole bunch of keys that all collide with each other, if I go searching for one of them or another key which is in collision with the keys at index 1, then of course the probing sequence will be identical because the probing sequence depends on my starting point. Any probing sequence beginning at index 1 will follow the same pattern of indices. Let's see, this one, back to here, and then finally all the way over here. If I start at index 1, that is the probing sequence I will encounter, whether I'm searching for 61 or 71 or 81 or 91 or whatever. Quadratic probing gives me a different probing sequence per index, but if I'm in the same index, I get the same probing sequence, which means I do end up clustered, but the cluster is related to the collision that started when I originally hashed my key. And so it's not as bad because, as we saw last time, if we choose our hash function wisely, we can expect that the number of things that hash to each value, on average, should be about alpha. It should be about n over m. And notice that alpha, we call alpha the load factor of the table. And that's a lot more meaningful in this lecture because it literally is the fraction of the table that is occupied. That is, it is the percentage of the table that is actually full of keys. And 1 minus alpha would be the fraction of the table that is empty. So the idea of it being a load factor is a great deal more concrete in a table where the keys actually live inside of the table as opposed to in linked lists. And also the idea of it being a load factor that, can be at most 1 is much more concrete because with chaining, it is actually possible with chaining to have alpha be greater than 1 because you can have more than one thing in every bucket versus with open addressing, alpha can be at most equal to 1. And I've told you earlier that you really should not allow that. If alpha actually hits 1, you should resize the table to open up some empty space or else things are going to get pretty nasty pretty fast. So here's an idea. Maybe I can actually diffuse the secondary clustering a bit. Okay, that's a typo. So it's pretty clear from the context that I'm talking about secondary clustering here. I was waiting for a typo in these slides, although I think there was already one. My idea is, just like how I was able to reduce the impact of primary clustering by defining my probe sequence to be different depending on where I start, or to at least, if I look at the set of indices, it depends a lot on the starting point, maybe I could do the same thing to prevent secondary clustering. In other words, maybe I could make it so that instead of the specific probe sequence that I use depending only on the hash value, because that's what's happening here, if I start at index 1, I follow the same probing sequence every time. Why not make it so the probing sequence I follow depends on the properties of the key? So individual keys, even if they both happen to hash into bucket 1, maybe could have different probing sequences based on some other property of the key, something other than what the hash function takes into account. Really what I'm sort of saying is, why don't I get a second hash function? Because we know that hash functions are a way of boiling down the information in a key of whatever type we choose into some number. What I could do is have two hash functions. One hash function that gives me my initial placement in the table, and a second hash function that moderates how I probe the table if the index I'm checking is full. And that brings us to a scheme called double hashing. So double hashing uses two hash functions, h1 and h2. We add one restriction, though, which is that h2 is never allowed to equal 0. And it's going to be obvious in a minute why that is. The probing sequence is then going to be, well, I start by looking at h1. h1 is the regular hash function, the one we've already seen. If this bucket is full, I then try h1 plus h2. Then I try h1 plus 2 times h2. Then h1 plus 3 times h2. And if I break that up into considering a step number I, at at step I, if I starts at 0, I'm considering h1 plus I times h2, and I take the whole thing modulo the table size. So hopefully you can see why I need this restriction. If h2 equals 0, then my probing sequence basically fully fails if any collision occurs, because if h2 equals 0, this term just gets annihilated, which means if I have any collisions, I end up in an infinite loop where I just keep probing the same index over and over again. Now in practice, it's very easy to make hash functions that are never equal to 0. What you do is make a hash function, like for example, if I have an arbitrary hash function g, what I could do is take that modulo m minus 1. So the table size minus 1, which means the values coming out of it are between 0 and m minus 2. Then I just add 1 to it, and I get a value that'll always be between 1 and m minus 1. And so there's a hash function that is guaranteed never to be equal to 0. So it's a very easy constraint to satisfy. Just be aware of it. Your second hash function must always be not equal to 0. It can be anything else. Ideally, it is a good hash function, so it distributes things uniformly, but it never will evaluate to 0. So uniformly among 1, 2, 3, 4, up to m minus 1. Now, if we assume that we've chosen two hash functions that are independent from each other, that is, they don't have any strong correlation in behavior, then I should expect, even if I have two keys that cause a collision in H1, so if both K1 and K2 have the same hash value, then I should expect they do still get different probing sequences. So I shouldn't need to worry too much about secondary clustering. So we'll try some double hashing examples. So let's start our earlier example over again. So I've already inserted these keys and no collisions have yet occurred. I've decided to use this as my secondary hash function. So I just take k mod 12 because the table size is 13. So going mod 12 would be table size minus 1. Then I add 1 to it so that I'm guaranteed that my h2 is always not equal to 0. All right, so I'll do my insertion as usual. 5 is a freebie. It just goes into bucket 4. I then try to insert 35, and it hashes into bucket 5, but bucket 5 is full. So I then use my probing sequence. Now, if I evaluate H2 on 35, it comes out to be 12. Because 35 mod 12 is 11, and that plus 1 is equal to 12. Okay, so the first bucket that I check is actually the one before the one I'm already in. And that's a little bit chaotic, but that's what I get if I use a second hash function. I mean, hash functions are a way of introducing a little bit of chaos into my organization of data. Okay, so I try index 4. That's too bad. Index 4 is full. It's going to turn out this is actually not a very good initial, like this doesn't paint double hashing in a very good light, this first insertion. Okay, now I try 2 times H2. So H2 again evaluates to 12, or mod 13, that's equivalent to -1, and I try index 3. Okay, too bad, index 3 is also full. And then I insert 35 here. Okay, well that was bad luck. But we know with hash functions we sometimes have bad luck. Sometimes we have collisions. Sometimes the hash function that we use just produces an output that doesn't really work very well for our purposes. On the other hand, okay, I'll insert 89, that's a freebie. On the other hand, let's try looking at inserting 79. Okay, so index 3 is occupied as we expected, so we start our probing sequence. And notice that before, in the last couple of cases, inserting 79 required a bit of extra work. We had to probe a few locations. The value of my secondary hash function on 79 happens to be 8, and 3 plus 8, mod 13, is 11. And what do you know? Index 11 is empty. And so I'm able to insert 79 after only one extra probe. So I can't put it in the initial location, but my second try is successful. So we saw a case where double hashing actually made things harder for us than quadratic probing, and we saw a case where it made things easier for us. Let's do a search. Okay, so I want to search for the key 18 in this table. So 18 hashes into bucket 4, and index 4 is occupied, so I start probing. And the first thing I check, oh, that's too bad, it actually happens to be bucket 11. So that's just an unfortunate coincidence. The secondary hash function evaluates to 7, and it just happens that 4 plus 7 equals 11. So I check there, okay, too bad. And then I check the next one, so 2 times 7 would be 14, that all plus 4 is 18, that mod 13 is 5. I check index 5, it's full. So I keep looking, I then look at index 12, which is full, and then I look at index 6, which is full, and then I look at index 0, which is full, and then finally I hit index 7, which is empty. So the search for 18 sometimes required a lot of work. Back in linear probing, it required me to look at 5 indices, but for some reason, just bad luck, I guess, by using double hashing, the extra chaos resulted in me having to go all over the table and make this huge mess of different arrows before I found an empty space. But that's life, I guess. Using double hashing helps me to break out of clusters, but just because I break out of primary and secondary clustering doesn't necessarily mean that my probing sequence is always going to find an empty space quickly. Now, for the sake of illustrating the effect of double hashing on secondary clustering, let's go back to our earlier example with secondary clustering. So here's the case where I use the function k mod 10, and every single thing in my table actually hashed into index 1. And we saw that with quadratic probing, that was a bit of a problem. That is, we have a secondary clustering effect that required us to inspect every single thing in our table if we go searching for the key 71, which also hashes into bucket 1. And needless to say, if I were to use linear probing, I would end up with a similar problem. So with linear probing, I would just end up putting all of the keys next to each other. So of course, I'm guaranteed to have a cluster there. Let's go searching for 71 in this table. All right, so the hash value of 71 is 1, unsurprisingly. Index 1 is occupied. It doesn't contain the key 71, so I keep searching. And the very first thing I check is index 2, and that's empty. So while searching for 18 made a bit of a mess, searching for 71, which was an input that would have caused a lot of clustering with both linear probing and quadratic probing, this double hashing scheme was able to make quick work of that. I only had to check the initial index and one other index before I found an empty space, and the search terminated unsuccessfully. And so I hope that that sequence of insertions and those two find operations presents a sort of nice survey of the different cases we can encounter with double hashing. In general, the solution to these problems, so if I go back to my previous example where I had to look at pretty much everything in the table, more than half of the things in the table when I search for 18, really the solution here is I should have a bigger table. I'll bet that if my load factor was smaller, if I had a table of maybe size 15 or 20, or maybe not 20, let's do 19 or something like a prime number. If I had a table of size 19, I'll bet I would have found an empty space sooner. In general with hash tables, you can often solve a performance problem by making the table bigger. Just lower the load factor. The smaller the load factor, the more empty spaces there are. And we've seen by now that empty spaces are what make open addressing schemes fast. The more empty spaces and the better they're spread out, the sooner you find one, the faster everything is. You can't control where the empty spaces are in general because you don't know what keys you're going to work with. Even if you choose a random hash function, obviously that means the empty spaces will be in weird random positions. What you can choose is the table size. If you make the table bigger and your hash function is good, you should expect there to be more empty space and the empty space to be distributed relatively evenly. And that's one of the results I want to get to next. So remember from last time that under our uniform hashing assumption, the expected running time of an insert operation or an unsuccessful find operation, and recall that I can't just say the worst case find because we're not talking about worst case. I can't say the worst expected running time because that doesn't really make very much sense. So I'm just going to talk about unsuccessful searches because we do know that a successful search will take less time than an unsuccessful one. With chaining, we know that the expected running time, assuming n is greater than 0, because there are some sources that write this as 1 plus alpha to, whoops, that's a weird alpha, 1 plus alpha to allow for the case where alpha equals 0. I don't think we need that as long as, because we assume in general that when we talk about things asymptotically, we're assuming n is reasonably large, and therefore that alpha is non-zero. So if alpha is non-zero, we can expect that a search or an insertion or a find operation takes somewhere around big theta of alpha time. But formally what we showed was an insert or unsuccessful find requires inspecting alpha elements of the table in the expected case. Here's a result about linear probing. This is actually a very famous result, partially because it comes from a very famous computer scientist. Let me try that again. A very famous computer scientist, Donald Knuth. Yes, indeed, it's pronounced Knuth. It's not a silent K. And Knuth wrote a really important series of books called The Art of Computer Programming, which I was lucky enough to be able to consult for the sake of making this lecture because it actually contains a proof of this result, a proof that I do not think you terribly want to see in this course. And so under the uniform hashing assumption, if I want to basically consider what is the expected length of the probing sequence if I use linear probing, this is actually a result about linear probing. If I use linear probing, the expected length of the probing sequence for a successful search is this number. Now, it's hard to make heads or tails of exactly what this means. You can go try and evaluate it. What this is telling you is that basically, if your load factor is somewhere around 0.6, 0.7, you're probably going to have to look at maybe 2 or 3 elements. And that's, of course, a constant. Notice that if we can keep alpha at a constant, this thing is a constant, regardless of exactly what it's supposed to mean. For an unsuccessful search, it's this, which is a little bit larger. And what both of these are telling us as far as we're concerned in this course is that just like with chaining, if you can make alpha a constant, and since alpha is based on a parameter that you control, you are in control of the table size. If you can keep alpha at a constant, the expected number of probes with linear probing is also constant. So although we had some evidence today that linear probing has some disadvantages, like primary clustering, and I guess it's also impacted by secondary clustering as well, although it has those disadvantages, it turns out that the expected running time with linear probing is basically the same as it is with chaining, give or take a couple of things. And given the fact that when we work with linked lists, there's a lot of extra overhead that doesn't even take into account possible cache performance issues, linear probing actually is a very viable method of implementing a hash table. It does give you the same running time guarantees that you want in your expected case running times that you'd get with chaining. So the corollary there is, if we can keep alpha bounded at some constant less than 1, and of course when you're using open addressing it has to be less than 1, you can't make it greater than 1, then you do get expected case constant operations for all of your dictionary operations. So find, insert, and remove. So where does that leave us? Well, that means if you want to use a hash table and you choose your hash function wisely, you can get expected constant performance for all of the dictionary operations, either with chaining or open addressing. And that's with even the most basic open addressing scheme like linear probing. One of the benefits of using linear probing is, although it does have some disadvantages, it still gives you constant time expected performance, and it doesn't have any weird tricks up its sleeve. We saw that quadratic probing has a weird issue in certain cases, and double hashing, well, I guess that depends on being able to come up with 2 hash functions that behave correctly, that is, that are reasonably good hash functions. Whereas linear probing only requires the 1 hash function, the same one you might be using for chaining, and it still gives you expected case constant performance. So we're just about at the end of our hashing odyssey here. And so what I want to talk about at the end is some justification for why you might want to use chaining, why you might not. I mentioned in the last lecture that because I sort of intend to assign some exercises involving gathering data, I don't want to present timing experiments, and also that because we're talking about a search problem where things are expected to be really, really fast, it is much harder to draw meaning out of timing experiments unless you have all of the information in front of you, like you can look at the code. Because if I time the performance of a hash table, I would have to take into account like exactly how I'm implementing my linked lists. Is it singly linked or doubly linked? Because the time it takes me to maintain a doubly linked list could make the difference if I'm comparing chaining to open addressing. So as far as presenting a comparison, what I will do instead is I will defer to language standard libraries on the argument that if a particular hash table has been adopted by a major programming language that lots and lots of people, including all of us, might use, that is evidence that the techniques that that hash table uses must be viable. You would expect that those people have done their homework. And so we can, I guess, I don't know if the lesson I want us to take from this is we should let other people do our homework for us, but that is sort of what we're doing. We're standing on the shoulders of giants here. So if I look at the C++ standard library, the standard hash table collection types, there could be other hash tables in the library for all I know, but the standard hash table collection types are std unordered set and unordered map. And it's very common to see in languages that a set data type, to store a collection of keys that do not have duplicates that allow for fast lookup, a set is often implemented using a dictionary, just where the value in the dictionary is ignored. And I don't know if I blame them, because we've just spent several lectures in a row where we have sort of been disregarding the values of the dictionary. If you just store the keys and don't care about values, the dictionary is actually quite a useful data structure for storing a set where duplicates aren't allowed. And the same is true in Java and Python, it turns out, that they actually use their set types or just their map types with no values associated. So in the C++ standard library, the hash-based collection types are called unordered set and unordered map. And the way the specification is written implies that you pretty much have to use chaining for it. It does there are certain aspects of the documentation that do sort of hint that chaining should be used, but there's also some contradictions in the way the specification is written that forces the use of chaining if you want to be compliant. I'm phrasing it this way because it's not like there is one single implementation of the library. The C++ standard library is just a specification document. If you go to compile C++ code, you'll have some implementation of the library on your machine, probably one that came with your compiler. That is, if you use G++, the GNU C++ compiler, odds are you probably have the GNU implementation of the C++ standard library because, you know, those two projects reasonably have a bit of collusion. And what I learned about that doing some research, and I actually found a really interesting article that somebody had written about the way hash tables were implemented in various languages, and I'll put a link to it in the video description, and it's in the slide at the end of this deck of slides with all the other sources. What I learned was that in the GNU standard library implementation, it uses chaining, and it forces the table size to be a prime number. And we've seen over the past couple of lectures a few reasons why that's a good idea. So it uses chaining, not quadratic probing, so there's no reason it needs a prime number for that. But we saw that when you're designing hash functions, it's often very beneficial to ensure that your table size is a prime number. And so the library does that. It forces it to be a prime number. The table does get resized over time. You're actually allowed to specify what you want the load factor to be. So you can tailor when it does resize operations to maintain a certain amount of empty space. And what it does when it resizes is it just goes and finds a prime number that matches up somewhat closely with the load factor you want given the number of keys that you have. It doesn't do that by finding prime numbers from scratch. It does that because it, I assume, maintains some internal database of prime numbers that it can refer to. Now, what about Java? In the Java standard library, we've got java.util.hashset and java.util.hashmap. Actually, I want to go back one. I should observe, in the C++ standard library, if you want a dictionary that isn't hash-based, you will just use stdmap and stdset. Notice that we call the hash-based one unordered, and the non-hash-based one is just called set or map, because the non-hash-based one is a red-black tree, and it's maintained in order. So if you iterate over an stdset or stdmap, you can iterate over the keys in sorted order, because they're implemented with a self-balancing binary search tree. The same is true of Java. So in Java, you've got tree map instead of hash map, and that would be implemented with a red-black tree as well. So in the Java standard library, of which there is a standard reference implementation, there could be more than one implementation of it, but since the invention of the language, the maintainers of the language, which was a private company all this time, did maintain a standard reference implementation of the library. So we can actually say a lot more definitive things about how these things are supposed to work. And also, frankly, I love C++. C++ is my favorite, but it is true that Java does have a little bit of an edge in terms of how its standard library is documented in a lot of ways over C++. That is, the most common source of C++ library documentation is a sort of unofficial source, so like cppreference.com, which doesn't correspond to any standards body or anything else. It is a sort of unofficial source. It is officially maintained by various stakeholders, but not actually the standard itself, whereas the official Java documentation is maintained by the maintainer of the Java language. So like the C++ version, and I have a feeling that these libraries were being developed at around the same time. So the C++ library was developed between the 80s and the 90s, and the Java library was developed in the mid-1990s. I suspect that there was quite a bit of cross-communication. That is, they were learning lessons from each other. Java probably learned a few lessons from the C++ library. It did some things the same and some things differently. So it's not surprising that they have a lot of similarities. The Java hash map also uses chaining, and it also allows you to specify a target load factor. I noticed while reading the documentation, in the Java doc, it suggests that maybe you want 0.75. So I've been suggesting 0.6 all this time, but the Java documentation suggests 0.75. In its exposition on that, it does discuss the same things I usually discuss, which is that a higher load factor means a more compact table, but it means that lookups, you're likely to have more collisions and therefore lookups take longer. A lower load factor means a smaller table, which to some extent can increase performance, but after a while you get the law of diminishing returns, but it can result in higher performance. What's interesting about this, based on the article that I read, is that it turns out that the implementations that are used in the Java library actually always require the table size to be a power of 2. Now, this is not something that we want theoretically for hash tables. That is, there's no inherent theoretical benefit to using powers of 2. There are performance reasons and architectural considerations that mean powers of 2 can be helpful. So one reason why using a power of 2 for the table size is that means you can ensure that the size of the underlying array is also a power of 2 in terms of bytes. And that can be helpful for memory allocation reasons. So deep down at a low-level setting, when you're allocating memory, it's generally easier to allocate memory in chunks that are powers of 2 in size. Additionally, using a power of 2 does make certain operations faster, although it's unclear if that's really worth it given the complexity of the data structure. So if I want to compute modulo operations inside of a computer, if I'm doing something, let's say modulo a power of 2, like 2 to the 5 or 2 to the 7 or something, I can do that modulo operation with a bitwise masking operation, so a bitwise and that's way faster than proper division. So doing something modulo 13 or modulo 137 requires usually the same processor circuitry that you use for proper integer division, and integer division tends to be slower, so it requires more clock cycles. And of course, we're talking now about a very low-level optimization. So there are often cases where if you can find a way of taking things modulo a power of 2, you can save a trivial amount of time. And there are reasons why I would want to do that in certain cases. Like I do believe in that option as an optimization, and as somebody who does a lot of code optimization, I often do that, but I'm writing low-level C code. It's weird to see this in the Java standard library, and I'm not sure that they're doing it for that reason, because there are other things in the hash map implementation that are probably slower than they need to be. So it's weird that they're chasing individual clock cycles with the modulo operation and not trying to speed up other aspects of their data structure instead, but who knows. One other thing I noticed, at least in the article that I read, and I didn't have a chance to look at the code to verify this because, as I said previously, going and reading standard library code is not one of my biggest priorities in life in my free time. But it turns out apparently that the Java hash map is willing, it uses chaining, it is actually willing to go beyond a linked list for its chains. So instead of storing the contents of each bucket with a basic linked list, something that I said in the last lecture, we're going to assume we always do, although there are ways of generalizing, apparently it will actually use like a tree map instance if it notices the buckets are getting really full. So I suppose that means if you just juice the load factor, so if you demand that you want a load factor of like 500 or something, the library will detect that the buckets are really full and will automatically, I guess, switch to a more powerful data structure for searching, so a tree map. It's weird to see that because although that's valid and would lead to an increase in performance, I would argue that that's the result of using the hash table improperly. That is, if you have a hash table where the buckets are getting this full, then you're not really trying to benefit from the hash table in the way that all of the usual theoretical guarantees on hash tables would imply. You're trying to do something else. You're sort of abusing the definition of a hash table a bit. And so it's nice that it does this, but it's peculiar that anybody would find themselves in that special case. If you use chaining, you should want to be in a position where the buckets themselves have a constant size, let's say 3, or, they might have size 10 or 100 or something, but that's very unlikely. So it's weird that you'd want to provide for this case. But okay, Java's just going to Java, I guess. And then finally, Python. And I have referred to the Python dictionary over and over again since I introduced the dictionary data type, and it's a big deal. Python is a really amazing language in my eyes. So I do write a lot of code in C and C++. As I mentioned, I've admitted that I don't actually write that much Java in my day-to-day practice, unless I'm teaching a course, pretty much. But I do also write tons and tons of Python. It wouldn't surprise me if, in terms of number of lines of code that I write, Python is pretty competitive. Much of the work I do outside of giving lectures like this is writing C++, but on the other hand, I write tons and tons of Python code in the context of courses. That is, these lecture slides are brought to you by Python code, among lots of other things. So to generate these lecture slides, I wrote tons and tons of Python, and I think Python's a really fascinating programming language. And one thing I've observed about it already in these lectures is that Python dictionaries, that is the thing you get if you put two curly brackets next to each other in Python, that dictionary object is actually a hash table. And also, the Python dictionary type is used for all sorts of things behind the scenes. And so that hash table better be good. I would argue that the Python dictionary hash table is one of the most thoroughly optimized hash tables in existence. Now, certainly there are lots of other huge, large-scale applications of hashing. So, for example, if you're running a search engine or something, you're going to need hashing for that. that, or you're writing a database system. But what I'm arguing about the Python dictionary is it is a hash table that has had to be optimized for off-road use. I mean, if you're designing a hash table for a search engine, you have a pretty clear idea of what kinds of things you're hashing and how it works. Whereas a Python dictionary has to be able to work with data of all sorts of different types, even data types that some programmer came up with at 3 o'clock in the morning and had no idea what they were doing. So I often create objects that I want to put in a Python dictionary, and I write a really terrible hash function for them, and the dictionary still works. And so the Python dictionary objects have been sort of hardened. They've been made robust against lots of different use cases, including a lot of cases where some of the other code involved has been written really badly. And Python is supported largely by its dictionary type. So internally, besides as one of the fundamental data types of the language, inside of Python, dictionaries are used for really obvious basic tasks like looking up local variables. If you type a local variable into a Python interpreter, the way it looks up what that variable is and finds its value is it just uses a dictionary. Similarly, if you have an object in Python and you refer to the members of the object, so if I say, a.name, or I call a method like a.getName, then what's actually happening, the dot operator in Python, where you look up a name associated with an object member, is actually using a dictionary. The members of an object are stored internally with a Python dictionary. And so a Python dictionary is a really big deal in Python. And the reliance on dictionaries, the fact that so many language features are actually just dictionaries, is really powerful because it means you can manipulate the language in real time. Because everything's just a dictionary, that is what provides you the flexibility to do weird Python shenanigans like manipulating the members of an object whenever you want, because it's just a dictionary. It's not been baked in like it would be in C++ or Java. Java does support a certain amount of introspection, though, so to be clear. In C++, everything has to be handled at compile time, so of course, at runtime, you can't go around manipulating how objects look. But in Python, you can change the entire character of the universe as far as Python is concerned while Python code is running. You can do such bizarre things as changing the meaning of the int type if you want to. And so that's a great idea. And it's hash tables that make that possible. And the Python dictionary hash table is a pretty amazing thing. It is highly optimized for a wide variety of use cases. And it's even designed to handle use cases where the designer of the hash function had no idea what they were doing. So in Python, hash tables for dictionaries are actually use open addressing. They do not use chaining. They target a load factor of 2/3, so 0.66 basically. And the probing scheme they use is none of the schemes we've seen today. It's a specialized probing scheme that works around a lot of the issues with the probing schemes we've seen today, and also helps to defend against the case where somebody gives them a hash function that's terrible. So even if you use a hash function that's really awful, for example, where everything gets hashed to the same index, the probing scheme, as we've seen with double hashing, can help work around that to some extent. By using a probing scheme that relies on a secondary hash function, you can work around the situation where tons and tons of collisions occur with the primary hash function. And as I said, because these hash tables are so critical, they've been subjected to tons and tons of performance tuning over the past, 30 years or so since Python has come into existence, and they've even been optimized for cases where, in a typical hashing scheme, you would obviously have fixed a bunch of things, so cases where your hash function is bad. We know already that we don't go after the probing scheme or the chaining scheme if we end up seeing lots of collisions, because that's the hash function's fault. We just design a better hash function. I guess I should close by observing that when I say these things are happening in Python, they're actually happening inside the C Python interpreter. So that is the reference implementation of a Python interpreter. You could go write your own Python interpreter that doesn't use hash tables at all, for all we know, although that would be very weird. I think you pretty much have to use hash tables for dictionaries for Python code to make any sense. But the C Python interpreter, that is the one that contains these hash tables. All right, we've had tons of fun with hashing. Way more fun than any of us were expecting to have. Almost too much fun. So what are we going to do next? We're done talking about hashing as far as this course is concerned. We'll come back to the idea of hash functions a couple of times. We're done talking about hash tables. After having this much fun with the data structure, what are we going to do? Well, okay, I've got an idea. Starting with the next lecture, we're going to talk about my favorite topic in algorithms and data structures. It is a topic that gives rise to tons of interesting algorithms, tons of interesting data structures, and it is my favorite. So although I might have had a bit of too much fun today, we're just getting started with that. And I'm planning for our next topic to cover a lot of time. That is, I think it's at least 15 or 16 lectures at this point.